So we've gone over a lot of the meat, a lot of the bulk of what we spent time on in statics, which were loading, reactions, solving equilibrium equations over and over and over again, and those internal loadings. And all of that's going to be very important for us. But another super important topic are some of the final two topics that we talked about in statics. So that would be your centroids and your moment of inertia. Moment of inertia. So these are usually some of the final topics that we talk about in statics, but they're going to be really, really important as they set us up for a lot of the stuff we do in strength of materials. So if we recall our centroid equations, right? So we had some body and the centroid is just the point in the middle of it, right? An X bar and a Y bar. Those are usually our centroids. I drew mine backwards, but I guess I'm just an idiot. I don't know. So our X bar is going to be the integral of X dA over the integral of dA, although a lot of times we'll see it just as a summation. Right, summation of X times A over the summation of all the different areas. So use the integrals if you're given like an equation, maybe you have some graph of, I don't know, a y equals negative x squared, something like that, and you want to find the centroid for this shape, you would use an integral. Whereas if you were given something like an I-beam that's made of all of these different shapes, you would just find the centroid of each portion, find the area of each portion, and then add those together and divide by the sum of the areas. So that's our X one, and our Y centroid is exactly the same. You just sub out the Y, the X's for Y's. So Y bar, or Y centroid, integral of Y dA over integral dA. Or same thing, just the summation of the Y centroids of each shape times A, all over the summation of all of the areas. These are our centroid equations. And then similarly, we talked about moment of inertia, which, if you'll recall, doesn't really have like a real world exact meaning, right? Because it's usually something that has units of inches to the fourth or millimeters to the fourth, but it's a property of an area. It's a property of the geometry that will help us do some calculations in strength of materials. And there is an integral form for that, but in strength of materials, we're going to see a lot more often the parallel axis theorem form. So the parallel axis theorem is the one that states that moment of inertia about the x-axis is going to be the centroidal moment of inertia plus a times d sub y squared. And it's the same for the y, a times d sub x squared, where your centroidal moment of inertia here is typically bh cubed over 12. And for IY, it is hb cubed over 12 for rectangular bodies, where your A is the area of the body, and then dy is the distance from the y-axis to the centroid of the shape, or from the x-axis to the centroid of the shape. So we'll look at a couple of examples using these, but they're going to pop up again and again in this class, so you'll have a lot of practice looking at these things. So in this example, we want to find the location of the x centroid, so x bar. We want to find where that is in our little field of grass over here. So what we'll need to do is break this down into shapes, and then we can use a table to do these summations. You don't have to use a table to do these summations, that's just my personal preference. But our equation we're looking at here again is the summation of the x centroid of each little area times the area all over the sum of the areas. And the two shapes I'm going to break this down into. Again, you can pick the shapes yourself. You can pick if you want to do like one really big square and then subtract out a smaller area, or if you want to do two smaller squares, which is what I'm going to do. I'm going to break this out right here so that I have a 3x4 square I'm looking at. I'll call this area 1, the other one area 2, is this 1x2 inch square. So this is my area 1 and this is my 2. So now that I have those, I'm going to make myself this little chart here where I put the shape. I'm going to find the x centroid of each area. Sometimes you'll see this labeled as x or x tilde. The area of each of my shapes. Then I'm going to go ahead and multiply those together. So my first shape, my shape 1, my x centroid for this first shape is going to be halfway through the shape since it's a rectangle. If the centroid for a rectangle we know is halfway through. So the x location here, halfway through 3, is going to be 1.5. Okay, 1.5 x direction, 1.5 inches. And then the area of my shape is 3 times 4, which is 12. If I multiply those across, 1.5 times 12 is 18. Now look at my next shape. My shape 2 here has a centroid. Again, it's a rectangle, so it's going to be halfway through this rectangle. But I need to include all of this distance that came before it too. So it's not going to be just 1 inch. It's going to be this 1 inch plus the 3 inches that came before it, right? It's offset by those 3 inches before it. So my x tilde is going to be 4. And then of course my area is 2 times 1. Very easy, that's just 2. Multiply across is 8. And for my last step, all I'm going to do is sum everything down this table. The only two summations I really need though are these last two columns. I need the summation for A and I need the summation for x tilde A. So that's going to be 12 plus 2 is 14. And 18 plus 8 is 26. And I can plug those numbers into my x bar equation. So the x centroid is 26 over 14. Or, if I punch that into a calculator, 1.86 inches in inches. There we go. 1.86 inches. So not too bad, right? Mostly just picking out information from what you see. The biggest one is just breaking this thing down into shapes and then picking out all the information that you need. Now in this example, we're going to be finding a moment of inertia, but now we're going to be finding it about the y centroidal axis, right? So about y bar. About y bar here, sorry, not the y centroidal axis, just the y centroid. Y bar, the y centroid. Which if we were to draw that on our little diagram here, I'm just going to assume normal xy coordinates. Let's say that our y centroid is maybe about right here. So if I were to draw this, this is where my y centroid is located. But we'll notice that the axis that this is creating is actually an x-axis, right? It's parallel to the x-axis down here. So this is the x centroidal axis. Sometimes we see it as x prime. So the y centroid and the x centroidal axis are the same things. meaning that we're actually going to need to use IX formula, right? The moment of inertia about the x centroidal axis. And that equals IX prime bar plus a d sub y squared. So there are going to be two steps to this problem. One is we have to figure out what the y centroid is before we can do anything. And then we're going to create our table to set up this moment of inertia calculation. So the very first thing is, again, let's do this shape. Shape we have for our y centroid, it's going to be the sum of the y tildes times a over summation of a. So I'll need the y tilde for each shape, the area for each shape, and then that multiplication for those. So here I'm going to have my two shapes. I'm going to call this top one 1 and bottom one 2, since they're kind of already broken down into this 2x4 shape and this 6x2 shape. For my top shape number 1, I have the y tilde, so the y centroid of this shape, going to be halfway through this top here. So right here about, going to be 1 inch. This just here is 1 inch, and then we add those 4 inches that were below it. The y tilde is 5. Right? The 4 inches plus the 1 inch up to the center of that top bar. And the area, pretty easy, 6 times 2. 6 times 2 is 12. And then if I multiply these guys across, 5 times 12 is 60. Then for my second shape, my y tilde is going to be halfway through the 4. So halfway through this guy, half of 4 is 2. This distance here is 2. And then my area is 2 times 4 is 8. And then multiplying across here, 2 times 8 is going to give me 16. So finally, I just do the summations for these last two guys that I need. It's going to be 8 plus 12 is 20, and 60 plus 16 is 76. So my y bar equals 76 over 20, which comes out to 3.8 inches. 3.8 inches. So that's the location of this y bar here. It's located at 3.8 inches above the x-axis. So now that we have that, we can go ahead and set up a table with all of our moment of inertia stuff that we need. I'm going to make myself another table over here where I have the shape, same shapes I'm using, same shapes. But now I just need a little bit different information, right? So I'm going to need IX prime bar. I'm going to need the area, which I can just pull straight off of my last chart. So for 1 it was 12, for 2 it was 8. That's easy. I'm going to need dy, and then I'm going to do a times dy squared, right? So that way I can just sum everything at the end. So for my shape, my moment of inertia here is going to be that rectangular bh cubed over 12. And I'm using that because that's the basic moment of inertia for the shape, right? The area and the dy are what offset it from the axis, but this is the basic moment of inertia for the shape. That bh cubed over 12. For both of these rectangles, they'll both use bh cubed over 12. Right, and that's because we're doing the centroidal x-axis. The y centroid is the centroidal x-axis, but if we were doing the moment of inertia about y, then we would use hb cubed over 12. But for this is just plug and chug. Once you know that you have to use bh cubed over 12, again, it's in a bunch of tables in your table sheets, what these standard moment of inertias are. So bh cubed over 12, plug that into our calculator, right? It's our 6 times 2 cubed over 12 gives us 4. And then for shape 2, it's going to be 2 times 4 cubed over 12. 2 times 4 cubed over 12 gives us 10.7. Areas stayed the same. Now dy. dy is going to be the distance between y tilde and the y centroid. Right, this value is going to be the absolute value of y tilde minus the y centroid. It's the distance between that y centroid. So for our shape here, where our y centroid, y tilde was 2, but the y bar was 3.8. It's the difference between these two. So for our first one, it's going to be that 5 minus 3.8. Right, this centroid was 5, and then minus the y bar, 3.8, gives us 1.2. And then this distance between these two, if we subtract them, 3.8 minus 2, 1.8. So that's why we use the dy there instead of a y tilde or anything else. We use the d sub y to differentiate it because it's the difference between the axis of interest, which in this case is that y centroid, right, the centroidal x-axis, minus the centroid of each portion. So that's our dy. And then we'll go ahead and multiply these out. So we'll do this 12 times 1.2 squared. Punch that in my calculator, 17.28. Then we do 8 times 1.8 squared. 1.8 squared times 8 is 25.92. And then I like to just do these as a summation, sum them down the columns, because what I'm going to need in my equation here is the summation of all of these plus the summation of all of these. So my 4 plus 10.7 is 14.67. And then my final column, if I add the 17 and the 25, I get 43.2. So when I plug these in up here, all I'm doing is plugging in 14.67 plus 43.2. And then I punch that in my calculator. That gives me the moment of inertia is 57.9 inches to the fourth. Right, the units are always going to be a length measurement to the fourth power. So again, if you had any struggling with these, if you have any questions about these, try doing some more practice problems of these reactions, centroids, moments of inertia, internal forces. All of those things are going to be coming up a lot in strength of materials. So get comfortable with those, and we'll actually get started in earnest in our next video.